get the results, then you analyze what is the performance you are getting, then characterize it. Then with this performance, are you satisfied or not? Then if it is not okay, then again you go for design or simulation. So earlier, about 5 years back, this loop is not there. Once you design performance analysis carried out, straight away you go for fabrication. Then check the dimension tolerance and test and carry out the measurements for electrical specifications. Whether it is meeting the specifications or not, again you check. If it is not there, again go for improve design or improve the design or go for redesign. Then performance is okay. Then you see this antenna, and go for qualification test, because these antennas have to be used on a platform. So it has to meet all the environmental specifications. Then we go for qualification tests like high temperature, low temperature, vibration, then salt, depending on the application. If it is a shipborne, the salt current is very important parameter. So we go for that. If it is airborne, then vibration is very important. Depending on the application, we go for all the qualifications, well-defined procedures or tests are there. We will go for that. Then again check for its antenna, whether it is meeting all the requirements or not there. If it is meeting okay, then because all these antennas we are converting into a antenna 8 unit for direction binding, where more number of elements are there. Then you go for, you produce that number of elements and carry out again electrical stress streaming test and for remaining antennas. If they are meeting okay, then do deliver the antennas to the system integration. Here this is not there, actually wrongly it has come. If it is not meeting, again when environment is not meeting, you cannot use on the platform. Then reject or analyze and analyze the defects. Why the antennas failed? Then rectify that defect and again go for redesign. This is the cycle we follow in design of the antenna. Okay. But about 5 years back, these analysis tools were not there. Only limited analysis and simulation tools were there. Now, lot of simulation, that means computational electromagnetic softwares are available today to design and simulate the antenna. Basically, CM is a branch of electromagnetics that intrinsically and routinely involves using a digital computer to obtain the numerical results. Because we are using digital computers extensively in analysis of these antennas. The CM software is not only used for antennas, it is used for RF and microwave circuits and even packaging, even connectors. Everything now we can do in using simulation software. Suppose you take a ANSYS designer, all planar circuits you can design, that you can import into these HFSs, and as part of the antenna and this planar circuit you can simulate and see its performance. So another thing is, okay, this EM softwares are broadly classified as the application and the type of solvers used. The mostly used EM softwares are ANSYS HFSs, which is high frequency structure simulator, then CST Micro Studio, FECO Suite, this Agilent M Pro, Empire Excel, Del Cross Savant. Each software is having its own advantage and disadvantage. This ANSYS basically works on FEM. First, when they introduced FEM, because it is a frequency based, because when structures become electrically larger, the meshing requires huge meshing. The structure is required and takes more time. People were were not using for when the structure of the antenna is large in terms of wavelength. But the ANSYS has come out with now various options. Now they are using MOM also in the ANSYS in 15, and now they are introduced the HPC, high performance computing. So you can distribute the problem into different machines and solve that problem at different places and get the result. And it will take enormous amount of machine and do the large structures. Now we are also planning to purchase that HPC version. To another important problem what now we are facing, we are individually designing the antenna, perfecting the antenna we are getting. But once you mount this antenna to the antenna unit, head unit, which is about 1 meter diameter, so that still we have a problem what with existing facility. Not only that, now our users and system group is asking, what will happen if I mount this antenna onto the platform on an helicopter or on a vehicle? How it is performance is affected because of the platform. So that also they are asking. So with HPC it is possible. Now we are interacting with these HPC people. They have come out with all the solutions. Some examples they have worked out and shown us. We are satisfied with their performance. Now we are taking the action for procurement of this. So the general steps for EM simulation software is, first you have to generate the 3D structure. So how best you can generate this 3D structure, that decides your performance. So the software is also having all the facilities to import that structure from say AutoCAD, then the SolidWorks, you can import, and then you have to apply the boundary conditions. This is also one of the important, how best you can define this boundary condition for that particular structure. That gives you the required performance. Once you apply the boundary conditions, then you have to apply the excitations. Then solve the solution setup. At what frequency you want to solve this problem. Normally, when we are designing very broadband antenna, always we should take the solution frequency at the highest frequency. So this is the then it will give the best results at all the frequencies. Suppose if you, for the sake of speed and if you set up the solution frequency at slow frequency or mid frequency, your high frequency results will suffer. So that is why we have to take the solution frequency at the highest frequency. Then sweep, whether you want discrete sweep, interpolarity, then at what step that you can decide that frequency, then solve it. Then post passing. So I have found that the SANSYS HF is a very good post passing features. If this data is available, that's why it is taking more memory. But the total data is available. You can manipulate. Suppose you want to plot the gain versus frequency versus gain, you can plot it. If you want to plot the radiation pattern, you can plot it. Any way you want to present the data, that post passing is very good in HFSS. Most of the time we are using in HFSS. This CST Micro Studio works on FDTD method. So this is having some advantages and some disadvantages. This is PECO suite. This is also this is a hybrid server basically. It uses FDTD, FEM, then this MOM. All the servers are there in PECO. This software people are using for platform studies. When you put this antenna on the platform, what is the deterioration? But still we have some doubts. We are having the software, but always they will show the performance with 1 GHz or less than that. One monopole they will keep one place and they will show. But when we interacted with the people to show the performance at 18 GHz, when you put this antenna on a small aircraft or a helicopter or a vehicle, they are unable to show. Then this is a Agilent Pro. This can be used for 3D as well as 2D display. Then this can be attached to the Agilent ADS. But this is very useful for microcircuits. Then this Empire Excel is also there on software. But 2-3 times they approached us, but we have not used. Then this is an Savant recently is coming. This is very useful for platform studies which works on ray bounce technique. So this already I have told how we are going to do simulation using HFSS. This is just basic. So any book if you open, you can get this information. So now I will go one by one what is the type of antenna, how we have realized. So this is the one antenna recently we have developed 1 year back. Now the proliferation of the radars has come down, low frequency come down to 70 MHz to defeat the stealth, because now most of the aircraft developers or all armed forces, they are using stealth aircraft or stealth ships. So to detect that ships, stealth platforms, if you use micro frequency, because they are using radar and observation, various shaping techniques they are using to make it stealth, you cannot detect. So to detect stealth platforms, the radars they have designed now even at 50 or 70 MHz. And when radars are operating 70 MHz, most of the radars they will use vertical polarization, but these low frequency radars they will use horizontal polarization. But 70 MHz horizontal polarized antenna you can make, but it has to respond for both vertical and horizontal. So such antenna is as of today is not existing. UHF group and with lot of discussions we come out to a solution like this. This is one loop and this is a dipole. We combine together to make it to respond for both vertical and horizontal polarization, covering a frequency range of 72, 20 MHz to 500 MHz. We made this antenna, and because this we are going to use on an airborne platform, it should not present any aerodynamic drag. Again, we made it is in the form of a blade, and this like 4 or 5 antennas we are using in a combination to make this a DF antenna. Another requirement is the antenna should have good gain tracking and phase matching. So as you can see here how good they are matching in amplitude from antenna to antenna. So this now we are going to use in one of the current program of EW. This is another antenna covering 175 MHz to 2200 MHz. This is again safe to cover the low frequency and to counter the low frequency radar. Again, this is 2 loops we are using, and this is the dipole combined together to give the response for both vertical. This dipole covers the vertical polarization, this loop covers the horizontal polarization. You can see how good this measured ranging pattern, and this is the matching covering 175 MHz to 200 MHz. This is very broadband. This is one blade antenna we have developed for airborne platform for AWNC program. Again here the requirement is good gain and phase matching. You can see measured, this is both we have plotted amplitude and phase both within plus minus 10 degrees both in full frequency band we are meeting. So from here I will start whatever simulations we have carried out, how the results we got from the simulation. You see this is one mechanical antenna we require from 1 to 18 GHz. You can see here this is the bidirectional antenna. This is 2 cones with their apex very close. This is the excitation point where we are exciting the antenna to radiate. This is a broadband antenna covering 1 to 18 GHz. So making the mechanical or simulating is very easy. We have simulated, it is meeting all the requirements, but it is a vertically polarized antenna. To make it slanting and polarized, we have used wire grid polarizer. Normally we use 3 or 5 layer polarizer. So each polarizer grid used at 0, suppose if you are using 3 grid, 0, 15, 45, because output we want 45 degrees and the incoming is suppose this vertical means the another basic principle in designing the wire grid polarizer is the first grid should be always perpendicular to the incoming wave, because it is vertically polarized. The first grid should be horizontal, then next will be 15 degrees, then 30 degrees, 45 degrees. So if you go conventional method of designing this polarizer, we have to make 4 these grids we have to print on the copper substrate. Then in between there are layers that we call it a spacer. with low dielectric spacer, then this grids. So if you go conventional method without going any simulation, then this cycle is for one iteration, it took 1.5 to 2 months. We have to get the print the polarizers, designing, then assemble it, test it, then see the results. If it is not matching, again you have to go new iteration at another 1 month, 2 month cycle. Whereas using this simulation software, you have realized this model these grids using the HFSS, and there are various parameters in this. You can see one parameter is the grid width, the spacing between the grids, then spacing between the layer to layer. All these are parameters. Then one beauty of this HFS is it is having optometrics, parametric optometrics. You can put all these parameters into optometrics, and if you vary in steps of 5 steps, once you arrive to certain close results, then you can go 5 steps and optimize its parameters till you can get the required performance. So another beauty of this software is it gives all the details in the project tree. This is called project tree. Up to here it is a bimechanical antenna. Then these depend on the Rogers 1, 2, 3, 4. This is the grid layers. Then this is the rubber cell. This is the spacers. Then these are the grids. Then that means H grid, horizontal. First, what is grid? Then grid 15 degrees, 30 degrees, and 45 degrees. So suppose you want to change, just you can click it and change its position, that angle or that grid parameters. Then automatically it will changing and go on changing its lengths, and you can see its results in terms of radiation patterns or its impedance characteristics, frequency versus its return loss. You can plot and see. For each parameter it will plot one plot, and see, by seeing the graph which combination it is giving the required performance you can see. If this software is not there, it is difficult to design. Whatever some performance comes, you have to stop somewhere and you have to go ahead. Even with the detailed performance, you have to accept and go. But whereas now you need not compromise anything on the performance, you can go ahead. You see, this is the simulated patterns. This is the omni pattern. This is the omni pattern, as well as because I am going to use for slant 45 degrees. At lowest frequency only vertical polarization to horizontal small deviation is there. But you, above 2 GHz onwards, this I think 6 GHz because it is working from 1 to 18. 1.2 I have plotted, 6, 12 and 18. You see how close this VP and HP is giving the performance. This is at 18 GHz, 12 GHz, 6 GHz and 1.2 GHz. We require this antenna from 1.2 onward. So that's why I have shown here. So this is another antenna called equivalent spiral antenna, because now we are going to work on millimeter wave DF antennas. We require an antenna covering 80 to 40 GHz. So this is also simulated model. This curve we have